I'm Tammy Kolda, an applied mathematician, and this is Unlocking LaTeX Graphics. On this channel, I explain how to create graphics directly in your LaTeX code using a variety of examples. Today, I'll show how to create an isometric grid using TikZ. I use macros to set the angle, grid unit length, and total grid size, so any of these can be changed to suit your preferences. From these user-specified inputs, we use the TikZ math library with its trigonometric functions to compute all the other parameters that we need. For the drawing itself, I'll use something new, scoped clipping. This is a powerful technique for controlling the drawing area and much simpler than calculating the exact lengths of the diagonal lines that we need to create the isometric grid. We'll also use lots of loops and math expressions, so this is a chance to get familiar with those. The videos on this channel are based on my book, Unlocking LaTeX Graphics, as well as some bonus materials. I have here the preamble for our document for creating the isometric grid. The packages parskip, full page, and hyperref are just conveniences and not essential to what we're doing. The package TikZ is essential, and today we're using the TikZ math library to do a lot of our calculations. Before we actually create our grid, we have to do some setup. The picture I'm showing here is the basic building block of an isometric grid. It's a diamond with the line down its center. I'm going to use this to explain what the parameters are that we need to set before we can draw our grid. Red is being used here to indicate the parameters that I'm going to have the user set, and blue are the parameters that we're going to derive from that. Those of you who are mathematicians know we have some freedom in what are the user-specified parameters and what are derived. But I have chosen here the height of this diamond and the size of the interior angle. Let me go ahead and paste our code. The first thing I'm specifying is the vertical height of the diamond, which I'm calling in the picture V, and in the code I'm calling it VLen. The second is this interior angle theta, and I'm calling that iso angle in the code. From these two parameters, we can determine the other key parameters using trig functions. For all of these, I'm using pgfmath set macro. Some of them I'm just directly setting the values, but then for these others, I'm doing calculations. So first I'm creating an intermediate variable called ang, which is just theta divided by 2. And then I'm calculating the value of the diagonal length and then the value of the horizontal length. I'm also having the user specify the number of vertical segments that will be stacked one on top of the other, and then the number of horizontal segments, which will go left to right. I am requiring, just for my own convenience, that the number of horizontal segments be even, because as you can see, my building block is 2 times hlen, and that will just make some of the loops easier to have that be half of the size of the diamond. I also compute the size of the block using these values. So X max and Y max are the total size of the grid. I draw the outline of that using this command here, and so this is where we're going to draw our grid. Our next step in drawing the isometric grid is to add the interior vertical lines. We're going to do this inside of a scope, but I won't explain why just yet. We'll use loops to create the line. So let me paste the code so that you can see it here. We're going to loop from 1 to hh minus 1, but we need to calculate this hh minus 1 before the loop using a pgfmath macro. So I'm just setting that value to be ii. And then we draw each vertical line, starting at a point that is a multiple of this horizontal segment length, and then going up a distance of y max. When we compile that, we get our interior vertical lines. Next, we'll add diagonal lines that go rightward from the bottom and top of every even vertical segment. Let me show you the code. We first have to calculate this value dvlen, which is the maximum length we might need. This is 2 times the number of vertical segments times the diagonal length. When I compile that, what we see is that we get lines that extend past the edge of our picture. Let me make that a little bit smaller so you can see it. This is what we need to fix. So the way that we're going to fix this problem is by specifying a special clip path A clipped path fixes the drawing region and everything outside of it is clipped. We are going to do this inside of a scope so that it only applies to our grid and not any other part of our graphic. So we paste this code here, and I'm using this path with clip, and then I'm setting it to the size of the rectangle that we want everything to be drawn inside. When I recompile this, it now magically clips everything to stop at the edge of this clip path I've specified. Okay, I've resized our graphic so that you can easily see it. And now we have to finish the grid with the diagonal lines extending up and down from the left side. This will fill in the remainder of the grid. So let me paste that last bit of code here. We're setting the macro JJ to be VV minus 1. So we're going to go up and down between all the vertical segments here. And then I'm calculating how long the diagonal length should be. This time it's a little bit different. It's the number of horizontal segments times the length. So let's see what happens when we compile that. Now we filled in the rest of our grid. Now that we have this infrastructure in place, we can change the parameters. For example, I can change this vertical length to 1, and now we'll have a smaller vertical height for each of our cells. I could change the number of horizontal and vertical segments to be 8. And then maybe I could even change the angle to say 45 degrees to get narrower diamonds. So these are all things that you can play around with. I'm going to go ahead and revert those back to the original values for the rest of what we're going to do. One thing you may want to be able to do now that we have our grid is have easy access to those intersections without doing a bunch of calculations. So what we can do is do the calculations up front and set up coordinates. Let me go ahead and create our coordinate code here and compile that. What I'm doing is I'm labeling each coordinate as I dash some I index and some J index. For the even values of our parameter I here, I have I plus 1 indices that I have to draw. So I have to go from 0 to the number of horizontal segments. When it's odd, I only go from 0 to VV minus 1. So I have a PGF set macro that uses an if then else statement. So if I is even, it sets JJ to VV, and otherwise it sets it to VV minus 1. Likewise, if I is odd, I have to shift my coordinate up by 1/2 of the vertical length. So this FF is an offset, and it's 0 when I is even, and VLen divided by 2 when I is odd. And then here's my loop here. I'm placing a coordinate. And then just so you can see it for now, I'm placing a node. But once you're done with that, we'll comment out this node. And now we just have all our coordinates labeled. Now that we have our isometric grid and every intersection is a labeled coordinate, we can do something with our grid, such as draw isometric coordinate axes. Let me paste some code to do that. I use a scope, and I'm shifting it to the desired intersection point, I-3-2. I'm also using the every path and every node to specify the style for the lines I'm drawing and for the nodes I'm putting. I draw each of the coordinate axes, and then I'm using position equals 1.25, which is a little trick to position the node past the end of the line that I'm drawing. This is a fun trick with the position key. I hope you enjoyed today's episode showing how to use math calculations, loops, and clipping to create an isometric grid. I include a link to the overleaf document that I created today in the show notes. If you found this helpful or interesting, please click like or subscribe. If you have TikZ or PGF plots questions, please post them in the comments. If you want to learn more, please check out the other videos. I also have a book, Unlocking LaTeX Graphics, available for purchase at major book retailers. Thanks for watching.